All right. So we had the quadratic formula written out for this yesterday. I trusted that you guys knew where to put all the numbers for the quadratic formula. So today I just want to talk about the numbers that you actually get when you put it into the quadratic formula. So we do get two answers, as you would expect, because you got the plus and minus. They do actually both end up being positive. Yesterday I had mentioned that one would probably be negative. In this case, they are actually both positive, and I want to talk about why. Okay? So we get so we get 0.0737 seconds, so a really small one, and we get a pretty big one. So we get 27 seconds at 0.154. Okay? Why do you think we get 2? The plus and the minus, yeah. But what do these two numbers represent? What do you think? Okay. I want to talk about what this equation is actually really solving for. Okay. Essentially what it's trying to find is we have put a position into our equation, right? Namely, this position right here, that point that is 20 meters. And we've said, okay, math, give us when we will be at this point, okay? We have told it that we have a constant negative acceleration, right? This is going to behave just like gravity. So what does it do? Sorry. What does it do if it has that constant negative acceleration? So this is going to be like, let's say that right here is our distance that we're looking at, right? Does it pass that point twice? Yeah. So these are the 2 times that it would pass that point if it continued to have this constant acceleration. Okay? Make sense, kind of? Okay. So this is that first time that it will pass it. Because it's going 68 meters per second and it's only 5 meters away, of course it's going to pass the point with less than a second, right? Yeah? So it does not take very long to go that 5 meters from here to there. Okay? The second time is how long it's going to take for it to go all the way out here, slowing down the whole time, stop, and turn around and come back. Does that make sense? Okay. Now, if this were friction, like we kind of talked about it being, with the negative 5 meters per second squared, friction does this weird thing where as long as you're moving, you actually have a constant value of friction. Okay? So you would have a constant acceleration the entire time you're moving. Once you stop, however, your friction actually changes. It goes from kinetic friction to static friction. And static friction is actually bigger than kinetic friction. And static friction is going to be exactly as big as it needs to be to keep you standing still. Okay? So if this acceleration here were from friction, we could safely say it's never going to turn around because of the way friction works, right? So we would know that the first time and only time it passes this point right here is at 0.0737 seconds. Good? Now, if this were like a magnetic box, and this were acceleration from a magnetic field, and we'd actually gotten it, you can do some tricky things with magnets to get a constant acceleration from a magnetic field over a long range. If that were the case here, then this would turn around and come back, right? It'd also probably go right back up the ramp, because when it gets back to there, if this truly is a constant acceleration, it's going to be going 68.7 meters per second. So it's definitely going to go up the ramp at least a little ways, right? Yeah? So this is kind of this idea of what physicists like to call boundary conditions, okay? Where you look at the math and you say, okay, this is what the math's giving me. Now I have to apply the situation at hand to the math. Does that make sense? Kinda? So you have to look at what physics is behind it, and then you have to take that and say, okay, do both of these answers make sense? Does only one of these answers make sense? Okay? If you get no answers that would make sense with the physics, you've probably done something wrong in the problem. Good? Do you guys have any questions on this? No? Okay. Boundary conditions are important in mechanics, which is what we are mainly doing this year. They become indispensable when you get into E&M. Okay, so electromagnetic physics, if you go on to take that in college, your boundary conditions are very, very important. Especially when you start doing integrals and actually doing calculus-based physics. Your boundary that you're talking about is probably where you're taking the integral over, okay? So integrals work being taken over an area or a volume, depending on like 1D, 2D, 3D integrals. And so that volume or area that you're taking the integral over is generally your boundary condition. Does that kind of make sense, vaguely? Yeah? Okay. So boundary conditions are important. They are important here. They will get more important the deeper you go into physics. Any questions? No? Okay. Cool. We're going to end the stream then.